Welcome to this first introduction to data structures. This introduction will have two parts. In this first part, I'm going to talk about abstract data types and their relation to data structures. And as an example of an abstract data type, we're going to see stacks. And as a data structure that implements stacks, we're going to see dynamic arrays. And then in the second part, we're going to see another data structure that implements stacks, namely linked lists. And as additional abstract data type, we're going to see queues. So, why do we care about data structures and what is this all about? Let's take this example here. So, we have two possible ways in this example to store a set of numbers, either as a list, as a Python list, or as a Python set. Now let's assume I want to search for a certain number, and I want to do that very often. Then if we would be using a list, then this takes linear time in terms of the number of elements that are stored in the list. If I would be using a set, then it seems to, so this is a blue curve down here, it seems to be taking constant time. So if searching is what I care about, then I could be using a list, but I should be using a set. So it matters how I'm storing my data, what kind of data structure I'm using. Okay, so let's get started with abstract data types and data structures. So a data structure is simply a way that I store and organize my data so that I can do certain operations fast. And the operation that I will want to do is modifications, so inserting or deleting data, and then certain type of access operations, like for instance the searching. And we're going to see in this video as an example a dynamic array. In the next video we're going to see linked lists, and there are many more, and there will be more videos about, for instance, hash tables, heaps, and so on. So that is a data structure which already says how I'm storing the data and also specifies the methods that access and modify the data. The abstract data type, in contrast to this, simply describes the functionality that I want to have. In contrast to the data structure, it does not yet say how I'm getting that functionality, it just says what I want to have. So for instance, an abstract data type could simply say, okay, I want to be able to insert data into my data structure, I want to be able to delete data, and I want to search. So in this way, we would say which functions we want to have. We would not yet say which data structure we're going to use to implement that. And that's really everything. There's not more to be said about abstract data types. So there's not kind of anything magic behind it. It's simply what we use to describe the functionality that we want to have. And we always do that first. So we always say first what functionality we want to have, and then I'm going to show you a data structure that gives us that functionality, or possibly several data structures with different advantages and disadvantages. So, abstract data type functionality, data structures say how we implement this functionality. And for that we have to think about how do we store the data and how do we implement the algorithms for the operations that we want to have. So for the access and for the modification. So why do we separate this? So the reason is that it allows us to separate functionality and implementation, and that allows us, for instance, to focus on solving a problem instead of thinking about the implementation details. For instance, when I solve an algorithmic problem, I can say that I need a way to efficiently insert, delete, and search, let's say. And then at that point, I can focus on how I solve the problem and keep the implementation details separate, which in particular means that I can also plug in different implementations. Also, I avoid that specifics about the implementation are used in my problem, because I very cleanly say I'm simply using this functionality and I'm assuming that I can get it efficiently. It also allows us to change the implementation in the background. So we can optimize our data structure to get faster and faster, let's say, search operations. And we can also use different implementations depending on what is important. Generally, I mean, when we design software, it's good to kind of split so large programs into smaller modules, and this modularization is kind of part of the principle that we're using here. Let me give you some examples of abstract data types and the corresponding data structures. So today we're going to see stacks, and later in the next video queues, and as an implementation of these dynamic arrays. An alternative implementation are linked lists, and we're going to see which advantages and disadvantages they have. A different example, for instance, are dictionaries. So dictionaries, you might know the Python dictionaries, and those are implemented. So the data structure in the background is a hash table. And more examples are priority queues and dynamic sets on the side of abstract data types, and for instance, heaps and binary search trees as data structures that implement them. So let's start with stacks. So here you see a stack. So what is special about a stack? That whatever element is on top is the element that I can also access. More specifically, a stack stores a set of elements. I want to be able to support insertions and deletions, and I want to support them in a last in, first out scheme. So what does that mean? Whatever was added last is the one that is taken out first when I delete. Which operations do we want to support? We want to be able to insert and delete. Insert for a stack is called push, and removing an element is called pop, and pop also returns that element. And again, this is always the last element inserted. So the last element pushed is the first element popped. And then we want to also be able to say how many elements are still in the stack, so size, and whether the stack is empty. What are typical applications of stacks? So one example is a history of a browser, let's say, where you want to be able to go to the website that you just visited, and from there maybe to the website before that, and so on. Or undo in an editor, where you want to undo the last edit. So meaning you have your edits on a stack, and you want to be able to pop whatever the last one was and undo it. For recursion, to implement recursion, also a stack is used. That's maybe not really your concern, because when you use recursion, the language, the programming language, will handle that for you. Stacks are also often used as an auxiliary data structure when designing more complex algorithms. So it serves like a type of memory, you could say, of your algorithm. So that's a stack. And a stack is an abstract data type. So far we only said which functionality do we want to have. And now we want to talk about data structures that actually implement stacks. A simple way to implement a stack is an array. So here you see an array. Keep in mind, arrays have a fixed size. So an array is a fixed size sequential collection of elements such that I have constant time random access, meaning I can access the elements that I'm storing by their index in constant time. So this is different from Python lists, which don't have a fixed size. I mean, they have random constant time random access, but they don't have a fixed size. They are dynamic arrays, and we're actually going to see how Python lists work in this video. But more about that later. For now, the array has a fixed size. The idea of storing a stack as an array is simply adding elements from left to right. Now, we also need to have a variable that keeps track of where the last inserted element was. So I will have a variable called count, which simply counts the number of elements. And that means that the index of the last element is count minus 1, because if I have one element, it's on index 0. And this is how such a stack could look like in Python. I'm doing this as a class. If you haven't seen classes, don't worry about it. We're not using them heavily here in any way. Just think of a stack as some kind of object with methods. And one method is the method for initializing a stack. And that's the one we're defining here. Self always then refers to the stack itself. And a stack will have 3 parameters: a capacity, because I have to decide on some size, and let's say here my stack simply have size 20. It will have an array of numbers, which I call items, and then the count, which is initially empty. Okay, and now you could complain that my items list actually is a Python list. So to be very precise, I wouldn't need to keep the capacity fixed, but for the purpose of the example, let's assume this is an array and I'm stuck with this size. That in particular means that I can only insert, in this case, 20 elements into my stack before I have an overflow. So for a stack, I wanted to have 4 operations: push, pop, size, and is empty. Let's have a look at how we can implement these. So how do we implement size? I mean, that's easy. I mean, we're keeping this count. The count should correspond to size. So what we can do is simply we can say return count. And as long as we're maintaining our count correctly, this should work. Or what should we return for is empty? So there we just simply need to check whether the count is 0. So let's do that. We return whether self.count, so the count of that stack is 0. Okay, that was easy. Let's do push. So how do we push into this array? So in principle, what we want to do is simply we want to write into the array of items the new item. So what we would want to do would be simply to say self items. And now we have to think about where do we write to. The in count, if I use count as an index, that's actually kind of the next free index. So that's where I want to write. So count. I'm going to set that to our new item. Now I've inserted the element, but now I still have to update count. So now I still have to do self count. I need to increase that by 1. So this works nicely as long as there's space for the new element. If there's not any space left, I will have to return an exception. So I need to check if count is smaller, so self count is smaller than self capacity, then I can do this, otherwise I should raise an exception. Let's do that. Here you see that if self count is smaller than self capacity, I'm doing exactly this. Write the element onto the corresponding position and increase the count by 1. Otherwise, I report an overflow. How do we pop? So to pop, we simply want to take the last element and return it. And the last element is not the element at count, because at count there is no element, but 1 index smaller. So what I would like to do would be to say, so let me first decrease count. Now when I have decreased count, it's already, I set count correctly. And now I can simply return the element that I see there. Return, that is self items count. Note, I do not explicitly need to delete it. I simply forget about it by decreasing the count by 1. And again, we have to be careful, namely in the case that there's no element in the stack. So if there's no element in the stack, we cannot pop, we should raise an exception. And that's what we do. So if there is at least an element, so if self count is larger than 0, we decrease count, we return the element, the last element. Otherwise, we raise an exception. And that's a simple implementation of a stack. So what's the running time of these operations? So let's see. Size, I'm simply returning count. That is constant. Is empty, I'm simply checking count. That is also constant. How about push and pop? Here's a quiz. What is the running time of push and pop for a capacitated stack? A, both constant. B, push is constant, but pop is linear. Both of order log n, or both linear. The correct answer is A. Both take constant time, because for both push and pop, we change count by 1, we access an element, that's it. So now we have capacitated stacks, but initially we simply wanted to have stacks. So the capacity we only got because arrays have a fixed size. So if we want to avoid fixed size, then we have to do something different, or we have to change our arrays, and we're going to use dynamic arrays. So the starting point here is that the fixed capacity is not what we really want to have. I mean, it works fine if it's okay, but generally we don't know how many elements we eventually might want to have on our stack. The question is, how can we make an array with unlimited capacity? And keep in mind, an array as such has a fixed size. So here are two strategies. I mean, the naive strategy would be to say, whenever my array is full, I simply increase the size by 1. And the generalization of this would be the incremental strategy, where I say, whenever my array is full, I increase the size by C, by some kind of constant amount. A second strategy here is the doubling strategy, where I don't increase the size by a constant amount, but I always double the size. So if I currently have an array of size, let's say 16, and it's full, and I want to insert an element, then I make an array of size 32. The problem here is, what does it mean to make an array of a larger size? I mean, I cannot simply change the size of an array. So if I want to have a larger array, so if I want to resize my array, the option that I have is the following. I allocate a new array. So let's keep the example of 16 and 32. I make a new array of size 32. And now I copy the 16 elements that I had into my new array. And okay, I was making it because I needed space, so my 17th element I add then. Now that means anytime I want to resize the array, I actually have to make a copy of all of the elements into my new array. This is how this might look like. So here's the push operation now for the stacks, now using a dynamic array. So what does it do? We again have a capacity, just that the capacity is now not fixed. So whenever count already is capacity, meaning there's no space left, but now I want to insert an element, what I do is, and this is now the doubling strategy. For incremental strategy, we would be adding plus something. So for the doubling strategy, I multiply the capacity by 2. I make a new array of twice the size, and twice the size, because I already increased the capacity, is now of size capacity. I fill it with nuns, let's say. And now I have a loop which copies all of the elements of my old array into the new array. And finally, I'm going to set my new array to the array that the stack keeps. So I forget about the old array. I have my new array. Then I have enough space. So now I can insert my new item, and now I can increase count by 1. That is push. What is the running time? Now, if I have enough space, so if this does not trigger, I simply do these operations. So in that case, it's simply as before, and everything takes constant time. Now, what happens if I need to expand? So if I need to expand, then I need to do n copy operations. One copy operation takes constant time, so I'm spending linear time, and that it doesn't matter whether I'm doing incremental or doubling. So in both cases, so for the doubling strategy, my new array will be somewhat larger, but it will still only have size 2n. So even allocating that will be of order n. Now the question that we want to answer next is, which of these two strategies is better? Think about that for a moment for yourself. Also, what do you think is a better strategy? Always adding, for instance, always increasing the size by 5, or always doubling the size? So let's look at a graph, a schematic graph, in terms of the running time, or in terms of the operations, let's say. So on the left we have the add 5 strategy. When I push, most push operations take constant time. Only always after 5 steps I have a push operation that takes linear time. So here this is linear. In contrast, when we do doubling, then I have these expensive operations spread out somewhat more. But in both cases, the worst case is linear. When we need to decide which algorithm to pick, we often look at the worst case running time. So here the question would be, what is the worst case running time of push if I use the incremental strategy? And that is linear. But then again, if I ask what is the worst case running time for push for the doubling strategy, it's also linear. So this does not allow us to distinguish between those two strategies. Nonetheless, one is significantly better, and the way we're going to see that is by an amortized analysis. So what does that mean? We're going to look at n push operations. So we're doing push n times, and that will give us a total running time of n push operations, and we're going to call this T of n. And the amortized analysis now looks at the average running time of one operation averaged over this sequence. So what does that mean? If I do n push operations, the average time for a push operation will be this T of n, this big total running time, divided by n. So that is what we're going to look at next. Before we do so, a quick quiz. If we do n push operations, how often do we need to change the size of the array? For the incremental strategy and for the doubling strategy. So A, both constant number of times, B, both linear number of times, or C, for the incremental one, order log n times, and for the doubling linear times, or vice versa for the incremental strategy, a linear number of times, but for the doubling strategy only order log n times. The correct answer is here D. So for the incremental strategy, let's say we need to increase the size after 5 steps always, then the number of times we increase is n divided by 5 times. While for the doubling strategy, it's 2, 4, 8, and so on until we hit n. After how many such steps do we hit n? Log n. such steps. So here we already see that the doubling strategy needs to do the resizing a fewer number of times, and as we were going to see, this actually will make the difference. So now we want to analyze the resizing strategies. So how well do they perform in terms of an amortized analysis? So we're going to have two cases, the incremental strategy, and there we always increase by a constant c, or the doubling strategy, where we start with some constant size and always double from there. So if c, for instance, is 5, incremental, we get 5, 10, 15, 20. For the doubling, if we start with an initial size of 5, we get 5, 10, 20, 40, and so on. Here's once more how the Python code for push looks like. And what we're interested in is t of n divided by n. So to compute t of n divided by n, what we compute first is t of n. So let's start with the incremental strategy. T of n. If you look at this, so in all cases, so for each push, we will at least spend constant time for these operations here. But then always after c steps, we do this part, and that will be linear in the current size. So what do we get for the incremental strategy? So we want to calculate t of n. And the first c elements that I insert, I get O of 1 running time. But then with a c plus first element, I have to resize, and the current size is c, so resizing is order c, so let me write the c here. And then the next c minus 1 elements, I again get constant time because I don't need to resize. And then when I insert my 2c plus first element, I have to resize, and my current size is 2c, so that costs me 2c. And so on. Again, lots of 1s, 3c. Lots of 1s, 4c. I want to do this up to n. So this goes up to c times, and then essentially what do we have here? N divided by c, round it down, let's say, and then we have a couple of 1s left. Let's write that as a sum. So first of all, we can take all of these 1s together, these and these, these. They together, I mean the number of 1s that I have here is less than n, so I can simply bound this by an enter. This takes care of all of the 1s. Additionally, I have c plus 2c plus 3c plus 4c and so on. So that I can write as a sum. I goes from 1, 2, and then here the largest term was n divided by c, because n divided by c times c, that's n, so that's when we reach n. So up to n divided by c, let's say round it down. And that is I times c. Yeah, so I is initially 1, that's 1 times c, 2 times c, 3 times c, and so on. Okay, so let's have a look what we have. We have n, that's simply this n, plus c, so we can take the c out of the sum, times this sum here. So this is a arithmetic series, so you will know this, and that is simply c divided by c, n divided by c, times n divided by c plus 1 divided by 2. Let's put this together. We have n and plus, and let me write this as order. There's n here, so let me mark it. There's an n here, there's an n here, so that's an n squared. And then there's a c here, both in the denominator. and then that's c here. So overall that's divided by 1c and some constants. So that is T of n. T of n is of order n squared. What does that mean? It means that if we look at the amortized running time of one operation, which is T of n divided by n, then because we have a quadratic because T of n is quadratic, we get that the amortized running time of one operation is linear. And that definitely is bad. I mean, imagine I'm trying to sell you a data structure where inserting one element takes linear time. And the only thing that you can do is insert and delete the last element inserted. That is definitely not a good deal. Obviously, you would be hoping that Python lists are faster, and they are faster. I mean, what you want to have is constant amortized time. Let's see whether we can get that, and let's see whether we can get that with the doubling strategy. So for the doubling strategy, the analysis looks similar. We start with, so let's say initially our array has a capacity of c. So then again, we have 1 plus 1 up to, so c times. And now we need to resize, and that is of order c, the cost of resizing and copying the data into the new array. Now we again get ones, 1 plus 1. And okay, at 2c, so far it's the same. At 2c we again need to resize. So when we want to insert the 2c plus first element. But now we continue, and how many ones do we get here? We get 2c ones essentially, because the next time we need to resize is actually, so when we hit 2c, we resized to twice that, so to 4c. So we only need to resize at the point where we are at 4c and want to insert an element. And so on. And these groups of ones get bigger and bigger. I mean, they always double in size. I'm not writing them longer here, but they double in size. Because now this is already 8c. And 16c. And so on. So how long does this continue? This continues again until we hit n. So, and when do we hit n? So this is a series of the type 2 to the I times c. So how long does this now continue? It continues until this term times c would go beyond n. And when would it go beyond n? It would go beyond n when we have the following: 2 to the logarithm of n divided by c, let's round it down, times c. Because 2 to the logarithm is simply n divided by c, and n divided by c times c, that's n. And then we might have a couple of ones left, but that's it. So let's write that again as previously as n plus, because all of those ones, we have at most n ones, so that's n plus. And now we have a sum. And now I goes from c, so the terms here are always c times 2 to the I. C is c times 2 to the 0. So I goes from 0 up to log of n divided by c, round it down. Actually, to be precise, we will round this again. Okay, And how do we continue here? We again take the c outside. So this is n plus c times the sum. I goes from 0 to, let me write it without the rounding just to save space, 2 to the I. Now this is a geometric series with 2 as a base. So this is asymptotically corresponds to c times theta, and now simply 2 to the log n divided by c, which is n plus, so we have 2 to the log c times theta n divided by c, so we could even cancel that c. So we essentially have n plus theta n, so this is theta of n. So what does that tell us? You tell me. What is the amortized running time of one push operation when using the doubling strategy? Is it constant? Is it order log n? Is it linear? Or is it quadratic? It is constant because t of n is linear, t of n divided by n is constant. So what do we have now? We have finished the amortized analysis of the incremental strategy and the doubling strategy, and that allows us to compare those two strategies. What we saw was that the incremental strategy, the t of n was quadratic, so the amortized cost per operation was linear, while for the doubling strategy, t of n was linear, so the average cost, the amortized cost per operation was constant, and that's exactly what we wanted to get, so we should be using the doubling strategy. And this is also roughly how Python lists are implemented. I'll say slightly more in a moment, but you can think of this as what happens in the background of Python lists, in case you ever wondered. Given this information, you can also say more about the running time of certain operations on Python lists. For instance, append in a Python list actually exactly corresponds to the push operation that we were describing. So what is the running time of append? So very often we think of append taking constant time. That is actually not exactly true, but it is true enough in the sense that it's amortized constant time. But if you measure the running time of an append operation for a Python list, you will see that there are these jumps, these linear time jumps. And that is exactly because we are dealing with dynamic arrays. If we now, for instance, want to insert into a Python list on position I, so we want to insert x at position I. This also means that we have to make space for x. So this is not simply kind of replacing whatever is at I with x, but actually inserting that element and moving everything to the side. The amortized cost of this is n minus I plus 1. So if we are very much at the end of the array, then we don't have to copy that many elements. So if we're at the very end, it's like an append, so then it's constant time. But if we do it somewhere very early in the array, then the insert is much more expensive than the append. Pop I removes the ith element, so that is also order n minus I amortized. So this is maybe a bit of a surprise. Why is this also amortized? So we were only talking about push, and that push takes amortized constant time. But why does pop take amortized constant time? The reason is very simple. So far we only talked about how to grow an array. But in principle, if we had a very large list, array or list, and we remove many elements, we might want to shrink it again. And that's what Python lists also do. And then that takes, then again I have to do the copying, so then again I get amortized running time. And for instance, removing the first element, remove on a Python list, which corresponds to removing the first element in array, that actually takes linear time. And now you can ask, why isn't that amortized? Yeah, because also in the worst case, if I have to copy, that takes linear time, so it doesn't matter that actually different things are happening. It always takes linear time. So we can think of a Python list implementing a stack, and then pop corresponds to the actual pop, push corresponds to append, and sizen is empty. We can simply check the length of the list, and that's it. Now, if what I said is true, then if we measure the running time of a Python list and the running time of an append operation, then we should actually see these spikes. So that's easy to test. We can just do some experiments. I did those in the elementary data structures notebook, so you can also do them yourselves. And here you see the running time for one append operation, and indeed you see that once in a while we get these spikes. So this indeed seems to very clearly shows that append sometimes takes linear time. It's just so seldomly that it doesn't matter overall. We can also look at this in terms of amortized time per operation, and then indeed these few linear spikes don't show up overall. So overall we get something that is constant. Interesting observation here is this doesn't look like doubling. I mean, doubling, it would mean that the distance between these spikes always doubles. That is not quite the case. So Python lists don't double, but only increase by roughly 12.5%. Meaning also that this operation will happen more often, but the same analysis that we got with, if you remember the geometric series, also works with a smaller percentage. It's just a different logarithm that we get. And this is now in how it is in CPython. Obviously, there could be different Python implementations, but the standard CPython implementation exactly does this. So you can look at the list object there, and it will, there you can look at how a Python list is implemented, and you will see it's exactly what we just described, with some extra tricks, like for instance the 12.5%. But as I said, same analysis applies. So Python lists append takes constant time amortized. So what have we seen so far? We've seen stacks, we've seen arrays as implementation of stacks, but that gave us this fixed capacity. So then we looked at dynamic arrays, and for dynamic arrays we looked at amortized analysis to decide which of the insertion strategy, which of the growing strategies would be better, and we concluded that doubling is a better idea, or not necessarily doubling, but increasing by some percentage. So that's all for the first video. In the next video we're going to look at queues and linked lists. See you there.